Cool. So yeah, today we're going to talk about ZK on Bitcoin. I already have some specialists in the room that maybe you'll hear in the video, if you're watching the video. I'm always wondering, should I talk about UTXO? It always depends on audience, I guess. But maybe it's a good way to it's always a good idea to recap what the UTXO system is. And of course, we're talking about Bitcoin, so we have to talk about the UTXO for Bitcoin, because they're still in the UTXO system and not in the account-based system. Then I think I'm going to plug something called ZK Bitcoin that some people haven't heard about, but that was my project a while ago, which I thought was interesting on how to verify ZKP on Bitcoin. And then I'm going to talk about all the crazy stuff that's happening, which I think can be summarized as if you have a lot of constraints, maybe stupid constraints, none of that would exist if Bitcoin had shipped snark or ZKPs as an operand or in the Bitcoin scripts. But once you have these crazy constraints, people will go in crazy corners and will do crazy stuff. And you'll see that it's quite insane what ended up happening in this series of paper. And there's a lot of interesting cryptography from Garbled circuits to witness encryption and stuff that we don't usually see, I guess, in blockchains. Okay, so let's get started with UTXO. So if you think about Ethereum, it's an account-based model, everybody has an account, it's very easy, I'm paying this account, someone's paying my account. If you want to do multi-user applications, then an account is one application that everybody's using. In Bitcoin, you can't really do that. You're in I guess UTXO stands for unspent transaction output. And whenever you create a transaction, you basically consume some of these UTXO 1, blah, blah, blah. And then you create, let's call it inputs. So that's a UTXO, and then you create a bunch of outputs. And every input is a UTXO, so you're using it only once. It's consumable in a way. And then you create new ones, and these ones are going to be alive until they get consumed by another transaction. Or maybe they never get consumed because they can never get consumed for some reason. And the set of all UTXO, in my mind, I imagine that as a bag, is basically something you get by going through from the genesis, the very first transaction, up to 2 days last block in Bitcoin. And without doing that, we can't really know what's the latest set of UTXOs, because you don't know which ones are still available to be used and which ones have been used. And so when things are always moving like that, so you can sort of see a UTXO as an account. I guess that's one way of seeing it. But when things are moving from transaction to transaction, then it's kind of hard to create an application with a specific address that different people can use, because things are always moving. Whenever someone uses something, it moves. The other thing I should talk about is that Bitcoin has a Bitcoin script language. It's right here, Bitcoin script. And it's very limited in the sense that there's no gas, the idea of gas, because basically the programs you can write on Bitcoin are so small that it doesn't really care. It doesn't really matter. And so when you create a UTXO, you usually have a script in there called I think it's called the locking script. The name has changed over time, or there's different names. Some people call it the pub key script, because usually you have a public key that represents the account that you can pay to, or the hash of a public key, but you can pretty much do anything you want. You can have you can say whoever wants to spend me can spend me, and whoever is the first to spend, spend. You can say whoever knows the preimage of the hash can spend me, whoever knows that password can spend me, etc. But usually what you see is whoever can sign a transaction with this public key can spend me. But very limited. And so if we wanted to verify zero-knowledge proof on Bitcoin, this is where we would start. We would try to fit, Groth 16 proof or whatever, a ZKP. We'll try to feed the verifier circuit or the verifier program within this script. And whoever can run it So a transaction would come here and refer to that, output, and it would give some arguments to that script. So usually it's another script called the unlocking script that puts these arguments on the stack. So it's not very, doesn't do much. And people call it the signature script, because usually that's a signature that you pass. And so you could think that this has a gross verifier, gross 16 verifier, and this would pass as argument a proof. And if the proof verifies the script, you can run it in this script, then it unlocks the UTXO, and then you can spend it. So everything I'm saying is basically normal Bitcoin. There's nothing crazy in what I'm, like if you understand Bitcoin, you understand that. I'm not saying anything new. The primary is that this thing is limited. Every time I check the number, I forget, but there's a size limit if someone knows. You know. What's the?
It's
20?
Block size. So it's 4 megabytes.
4 megabytes? Yeah, so it's pretty bad. So yeah, you can really verify a gross 16, or you can run a gross 16 verifier in 4 megabyte. And it's limited by the block, so there's other stuff happening. The miners have to accept that mega transaction, I guess, and these kind of things. Okay, so that's the UTXO model, right? Things are hard, lots of limitation. Some people have proposed to, maybe I'll mention that after. Okay, so when I looked at the state of things, I guess it was 2 years ago, I was like, that's crazy. Nobody's verifying ZKPs on Bitcoin. I'm seeing some approach that I'm going to talk about, but it's quite complicated. I'm sure there's something much simpler that we can do. And so I took, with ZK Bitcoin, which I'm only gonna briefly mention for like 2 minutes, maybe less than 2 minutes. I just had an pure MPC approach where you would manage a public key with a MPC committee, so multi-party computation. And you could get inside this world, I guess, by sending Bitcoin to this key, so the committee key. And then if you wanted to spend it, you would have to send a proof to the committee, and they would have to verify it. The interesting aspect in that ZK Bitcoin scheme was that the committee didn't have to know about Bitcoin. You would just send them a transaction, and the transaction would have a hash of the circuit, like a verifier key, or a compiled circuit, I'm gonna call it like that. And so you would have to provide the actual compiled circuit, let's say, if there was a hash of the compiled circuit, a proof that verifies, and a transaction including all of that, and the committee would only sign it if they would see that and the proof verifying. But they didn't know anything about Bitcoin, and it just worked. And the nice thing also is that they could see the transaction spending the funds and who it was sending the funds to, and so you had this kind of self-introspection where you could see the state of Bitcoin, or at least a local state of Bitcoin, and you could do interesting like ZK rollups and bridges pretty easily. So we pushed that at the time, and we verified some ZKPs, but people were not happy. And it's not perfect because it was like really reliant on an MPC. And MPCs have these kind of weird threat models where it's, especially if you're a Bitcoin maximalist, you don't really like any trust assumption, and you want to like rely on Bitcoin itself. So anyway, I'm not gonna mention ZK Bitcoin because this was kind of the naive way of doing things, and there's elegant things you can do in this dimension. So BitVM was sort of the first one, I believe, that came and was like, okay, we have something more interesting that we can do, and it's an optimistic protocol. Optimistic meaning that in this kind of protocol, I lock some funds in this, let's say in a transaction, and then I come, or let's say it's this one, transaction 2. So I lock some funds there, and I want to, in a very simple scenario, like say that if I can verify some proof, then I can unlock my funds. That's the simple scenario. Basically, BitVM was like, okay, the optimistic protocol is that you're gonna just spend it in a way where the spending is like partial, so it doesn't really happen. And during that time, like you have to wait like 50 blocks or something. Like there's some time that you need to wait for. And then once that thing expires, you can actually spend it. You can spend it and you can actually send it to yourself or whatever. And during that time, someone can come and say, nope, I don't believe you. The proof is not valid. I'm actually going to spend it for my transaction. So that's a challenge, basically. And what occurred is that there was some fraud. So that's the idea of optimistic protocol. And you see that in optimistic rollups, etc. Optimistic, yeah. So something happens in the happy path after some time where nobody challenged it, it works. But if during that time someone decides to challenge the thing because there was some fraud, then they can challenge it. And then they can battle. Then the person that produced the proof has to like sort of prove on chain that the proof was correct. And that's the hard part. And so BitVM was like, okay, this we understand. And then the hard part, we're gonna basically have a circuit on chain. And the circuit is gonna be, maybe I shouldn't say circuit yet, but we're gonna verify the proof on chain, sort of. And the way we're gonna do it with this limitation is that we're gonna split the verifier in multiple scripts. Or at least that was the first naive idea. It was so naive that I don't know if it's even in the paper, but it continues in that direction. So I'm gonna repeat that. You have a gross 16 verifier. It's too big to fit in that Bitcoin script here, so I'm gonna cut it in many chunks, and I'm gonna put the first chunk here, and I'm gonna, or maybe here, let's say, in the scripts contained in this thing. Then I'm gonna put the second chunk in this script, then I'm gonna put the third chunk in this thing, and so you're gonna verify your proof across many transactions. They actually went further and it's even more efficient, but before I explain how they do it, I'm gonna explain how they chunk that circuit, which is, I think, the first interesting things I'm gonna talk about in this talk. Okay, does that make sense what I'm saying? Before I get into how can we split a circuit across many transactions?
Is the challenge period for the optimistic portion a certain number of blocks that's proportional to the size of the verifier, or like how does the time frame work?
Yeah, so that's a good question. So there's a challenge period. I don't actually know what, like there's different proposals. This is very instantiation. Depends how you instantiate that. But it's a good way to introduce something that I should have introduced called a time lock. And so in Bitcoin, it's an instruction, I guess, and you can say this UTXO is not spendable for until that timestamp or until that block or like something like that. And time locks are used all over the place. For us, in an optimistic protocol, so in this BitVM, maybe I should write it down here. If it's not big enough, I wrote BitVM. In this BitVM protocol and all of the series of papers that come after, they make use of time locks a lot. And time locks are used in a bunch of like, complicated protocols on Bitcoin, like Lightning Network and like channels and stuff like that. And you'll see that, so the challenger has to sort of go through that circuit with the prover, let's say. So they have to do that dance on chain where they sort of have to advance. And so to force each other to advance, they will have time locks at every transaction. So every time you move forward and you have to wait for the one of the peer to respond, there will be a time lock so that if they don't respond, then they get slashed or you win and you can withdraw the funds. So lots of time locks just to be able to make progress. And that's why the more complicated or the more transactions your protocol takes, the longer it takes because you have to wait. There's some weird clock where you have to move even slower than the clock of Bitcoin. Okay, so Bitcoin by itself has many, even more, more limitations are annoying. One is that the scripts are stateless. So when you have a script here that might use some variables with some values, whatever, you cannot reuse variables that are from that script. You just can't, right? Like a script is only scoped to that specific UTXO. So when you have a UTXO here that you execute as part of that transaction, all of the variables, whatever within that scope, disappear when you go to anywhere else in the network. So the first thing we're gonna try to solve is this notion of statefulness. Is it double L or one L? One L. Statefulness. where you're trying to carry variables across. Of course, we're gonna set some variables in the first chunk of the circuit. We're gonna want to keep them across in the second chunk, third chunk, whatever. It's kind of hard to imagine that it's possible this way, but basically what they use, so I'm gonna give you, I'm not gonna ask the question, but they use Lamport signatures, Lamport sigs. And before I even explain how they work or give some intuition, the idea is that Lamport signatures are one-time signatures. One-time sigs. I think they're the first hash-based signatures. I'm not too sure about the history of things, but at least they're one of the first hash-based signatures, if not the first. And so the one-time signature means that if you double sign, it's kind of like a double spend, like you shouldn't do it, it's really bad. And you can also detect it. It's very easy to, I mean, not that it's hard to detect a double signature in any scheme, but in this case, it's bad. And so what happens is that whenever you set a variable, maybe let's use an example. Here you have a variable called A, and maybe as part of the execution, you set A to like 5. And here you want to reuse the same value. What you do here is that you're going to assign the value, I guess the variable and the value. You're going to assign them using your public key, or use a different public key for different variables. There's different ways. And here you're going to assign the same value with the same public key. And so if you assign two different values, you're going to have a double signature, basically. And the idea is that there's going to be maybe another script, another UTXO, or maybe one of these UTXOs that you can slash, that you can spend, if you can prove that there's double signature. And that's really protocol. I'm not going to explain where that thing exists. It's based on your protocol. But that's the whole idea of how you preserve states across UTXO's scripts. Does that make sense? You always sign them using your Lamport signature. If there's a double signature, someone can see it. It's on the blockchain state, and they can present it to some UTXO, and then they can spend it, and they slash someone. And I guess very briefly, maybe I can explain how these work, because they're very simple. Imagine that you want to sign 2 bits. What you would do is you would produce 2 random values, A1, 4, I guess. This is for the first bit, this is for the second bit. And then you hash them. HA3, HA4. Right, so you have 2 random values per bit. This for 0, this for 1, this for 0 and 1 for the second bit. And you hash them and you publish this as your public keys. And to sign 1, let's say, you release these 2 pre-images. Or to sign 0, 1, you would release this one and this one. Or to sign 0, 0, you would release this one and this one. And you can imagine why it's not secure by yourself. And yeah, this works really well in Bitcoin, I guess, because we have a hashing primitive and all of that. Okay. Any question on the statefulness part? Then I'm gonna move to branching. So okay, so we have we can run stuff. We can run our big circuits, and we can chunk it and sort of keep these variables across. And I guess it's almost everything we need. We have a way to force things to move on with the Timelocks. But what we want is a way to like maybe conditionally execute different branches. So for now, like we're sort of unrolling everything. Like we have an algorithm that's unrolled, and if we take one branch, it doesn't matter. We have to have the code to like potentially execute both branch every time. And this is very tiresome, and obviously we don't like that. And so one way of dealing with that is actually this, and I need to talk about covenants at some point. How should I mention it?
You can mention Taproot maybe, like there can be multiple scripts in a single UTXO. It's And what country you can spend with?
Oh, Taproot. Okay, I'll mention Taproot. Okay, that's one way of doing it. So, how did I explain that before? So, Taproot is good thing to mention anyway. So and I guess we can just mention it briefly because it's not super important. But if you want to have like plenty of different scripts, by the way, thanks for that. If you want to have plenty of different scripts that you could potentially spend this UTXO with, there's this newish thing in Bitcoin. I guess it's not new anymore, called Taproot, where you can like have many of them and you can sort of choose which one you want to use. And I guess underneath the surface, there's Merkle trees and stuff like that, but it's not very important. So it sort of gives you some flexibility, but you still want to be able to So basically, the abstraction I'm creating here is that we're going to build a circuit on Bitcoin. That's the way I see it. And then once you can build your circuit, you can sort of do everything you want. But sometimes, well, I don't know. Sometimes I'm going to want this thing to take a different path. And I want this path to be transaction 4, let's say. And I want this path to be like either or, depending on branching. And so the way we do it, I guess we have different ways to spend. Of course, Taproot is one of the answer. The other thing is that once you spend a UTXO, for example, if you spend it here, then you cannot spend it here. So you have to take one of the path in that circuit. The other answer is that you can sort of agree on how the transaction graph is going to look like in advance. And so I guess this is something called covenants. And Bitcoin doesn't have covenants. There's a lot of discussion on how to have that, but it's not happening. And so most of the papers are doing something called simulated covenants, where basically there's some sort of trusted setup where everybody comes together and they pre-sign all of these transaction graph so that they sort of set in stone what transactions you will be able to take. They set the circuit in stone or like the game in stone. And then everybody deletes their private keys so that as long as one person is honest, only this path can be taken. If everybody's dishonest, then they can come back after the fact and they can say, oh, actually, let's add a new path. Let's add a new path here and let's sign a new transaction that can spend that one.
How does this setup look like?
How what?
How does this setup look like?
So setup is just basically there's a permission set of people. Like we all get together and we decide that we're gonna pre-sign all of that set, and it's going to look like that. The easy version is to have like a two-party. So whenever you think of these protocols, usually in papers, there's a two-party protocol. There's like a prover and a verifier or like a challenger. And there it's much easier. It's like, okay, we just need every transaction here has to be signed by both of us. And if this is a transaction that only the verifier can take, during the setup, the prover will sign it and give it to the verifier. And so when at runtime, when things are happening, the verifier can use the pre-signature from the prover. But it's the same idea. Simulated covenants sort of generalized to like many participants.
Is that what Garbled circuits come in like later versions?
So unfortunately, simulated covenants are like a thing in like every scheme. Like if you want to have like more than two people that set the stage, you sort of have to have that. It's the same even for two parties. So you cannot really get away from that. Garbled circuits are going to help us somewhere else. Okay. Did I forget to mention anything? Any questions?
When you have this set up and they're signing on like the flow essentially, not the specific transactions of what would be happening, and they can keep reusing that even if like more than once.
Yeah, so the way you can see that is that they're signing a circuit. So they're signing a bunch of transactions that haven't been posted on chain yet. And it looks like a circuit where every transaction is kind of an aggregate of fan in like many to many, fan out many, n fan in and m fan out gates or something like that. Or it's an aggregate of many chunks of many circuits because you have many UTXOs in it. I don't know if that makes sense.
I think so. It's like a function that like maps to many things. It's a many-to-many function, and it doesn't just get used once. You don't fully define what the transaction.
You only use it once. So every time you use a transaction, you can only use it once. It consumes part of your circuit, so it consumes the UTXOs, so chunks of circuits, and then it produces new ones.
So you have to do the signing once for each time that you would want to run this flow.
More than that, like you have to know the whole transaction graph, like the whole circuit in advance, like the whole program in advance. And so you might sign like, I don't know, hundreds of transactions, thousands, depending on like how big your protocol is.
For instance, our bridge pre-signs like 100,000 transactions per deposit. So like, yeah, a bunch of these transactions gets pre-signed per deposit.
So C3I is 100,000 for the record. I wanted to mention something else, but I can't remember. Anyway, so with these things, I think we have, unless I'm missing something, we have all the stuff we wanted to sort of chunk a circuit and like execute that circuit across multiple transactions. So now back to BitVM 1. So they're like, okay, we have this optimistic protocol. There's some Bitcoin locks in this. We already agreed in advance that if there's a proof that verifies, you can unlock them. And we have this protocol where the prover can come and say, hey, I have a proof. Here's my proof. And if the time lock expires, then I'll get there. I'll be able to withdraw them for real. And during that time, there's a challenger that can come. And if they don't agree, they will run the gross 16 verifier. Running the gross 16 verifier is too much. So there is another, I'm going to ask you the question, but I want someone that doesn't know to answer. If you have a circuit or program and you can execute it entirely, but you don't want to execute it entirely, how do you find the point of disagreement in that program? How do you find more efficiently, rather than executing the whole program, how do you efficiently find the point of disagreement in this execution? You can think of it as an execution trace.
And it's a stack-based system, right? The program is stack-based VM or something.
Well, actually, it doesn't even matter, right? Like in any type of...
There needs to be, yeah, state. Yeah.
We could think in like different types of program.
Can you set like breakpoints?
Yeah, I mean, imagine that you have all the breakpoints of the execution, and we have all the chunks of the circuit, right? So we can sort of jump anywhere. How do you decide like where we actually disagreed on like the execution that happened? I'll give you 15 more seconds. Okay, I'll tell you the answer. A bisection, a binary search. So, instead of like re-executing the whole thing, you just shoot in the middle and you're like, okay, do we agree on this execution, yes or not? If we agree, then we look at the second part and we shoot in the middle and so on. If we disagree, then we look, okay, where do we disagree? And you look at the first half and you try to find the point of disagreement. At some points, you will find a transaction that implements that part of the circuit, the gross 16 verifier where you disagree, and the prover won't be able to prove that this is the thing they're claiming to be. Up to the input or the output of the computation. So that's, in my memories, that's how BitVM 1 does it. There's a bisection game, and so it's still quite a lot. I think BitVM 2 is sort of the same. There's some optimizations in there, but I don't remember exactly how. And that bisection game is still like quite massive, and it still kind of sucks. Cool. Any question? And then I'm going to jump to BitVM 3 and then Babe, which are the last. Yeah.
So when you find the place that you disagree, how do you say that it was invalid? Do you like look at a step and say that you can't?
So basically, in the UTXO, there will be a script that implements that execution of that part of the cross-16 verifier. And let's say that, I need to think about that, but let's say that you disagree on the inputs of that execution. So then you need to figure out, okay, at what point does the input become different from like well, let's say that input is wrong, right? Like the prover is saying this is the input of that chunk of the circuit, but it's wrong. Then you have to figure out where, considering that they committed to the inputs, where did that input give something different? So you're gonna have to like basically execute everything from the input to that point of disagreement. Or you could do it from the output to the point of disagreement.
You're
Could do
doing
the
execution as opposed to comparing two stack traces?
You're not really. You have to execute something at some point, right? So first, you're just trying to minimize the execution you're going to do. So first, you're trying to figure out where do we disagree. Once you've shown where the point of disagreement is, you can see, okay, how did we get to that disagreement? And then if it's an input that's different from what we agree on, then we have to execute all the beginning up to that input. I guess if it's an output, you have to execute all the end of the, or if you, I don't know if that makes sense.
I mean, I guess like if you agree on the inputs, like you can execute one step and see whether you get to like.
Exactly. Yeah. At some point, for example, if you run the very first scripts, you cannot disagree on, like if the prover is saying this is the result on these outputs, you can just run the very first chunk and you can see, no, that doesn't match what the prover is saying. Right? And so you can extrapolate with like.
I see it as a verifier, you want to force the prover to sign both input and outputs of the incorrect chunk. So you start from the middle, now the prover needs to sign the middle state. So if that middle state is correct with your off-chain execution, then you ask the other part. You go to the other part and you ask the middle of the other part. And with like log n steps, you can force the prover to sign inputs and outputs of the incorrect chunk, and then you prove it on Bitcoin and slash the prover.
So you slash as soon as you show it was an invalid signature.
As soon as it shows, it signs, yes, inputs and outputs of a chunk that is incorrect.
Makes sense? And I guess you can think about it, but you sort of have all the ingredients here. Like you can, set like sign some stuff. You can set variables, which is kind of like committing to these variables. You can execute things. The bisection is just like what circuit are you implementing on top of what we created, I guess. Cool. All right. So this is BitVM 1 and 2. I guess I can also mention OP-cats. There was like, okay, can we verify Stark proofs on Bitcoin? And we have to do a lot of Merkle trees in Bitcoin. And what would be cool to do Merkle trees, at least that's my understanding, would be to have OP-cats. Unfortunately, I think he was removed from the Bitcoin script sets to concatenate stuff, to like hash them. He was removed at some point because I think Satoshi thought there was like a DOS attack or something like that on it. And then there's a fight right now that's happening on like, can we reintroduce OP-cat? No, we should not reintroduce it. So yeah, if people have been fighting for years to just introduce like a concatenation operator, you can imagine that snarks are never gonna have like their own operator on Bitcoin. Okay, so let's talk about BitVM 3 and Garbled circuits. So BitVM 3 introduced a different way of doing things, which is we're still doing too much on-chain. Instead of doing so much on-chain, we're gonna use something that's not a time lock, but that's a hash lock. And a hash lock is basically you're putting a hash in a UTXO, and if you can produce a pre-image, then you can spend the thing. And it's used in all sorts of applications as well, but you know, put this thing in a UTXO, whoever can produce the pre-image, gets to spend the UTXO. And so it's starting to be kind of messy, but let's put this thing here. So whoever can produce the M, actually let me remember who's producing the Okay, so as the prover, you come and you say, I'm gonna lock my phone, but later on, I want to be able to spend this stuff. And I'm gonna give you, so here's the secret, I'm gonna give you something. It's called a garbled circuit. I'm gonna explain to you what this does. Garbled circuits. You can think of it as a circuit, okay? So you can do some execution and stuff like that. But the nice thing is that it's not for you, it's for someone else. So it's a two-party computation thing. But the way of thinking about it in this context is that you're sort of doing the two-party computation in advance, or I'm doing that, and then I give you the rest of it, and then you can evaluate that by yourself. So unlike a zero-knowledge proof where you I guess you do it locally myself, here I do it, and then I let you do the second part of it, I guess. I don't know if that makes sense. Maybe I'll re-explain that again. But I'll tell you what's in this garbled circuit. It's a function that takes a proof. It implements gross16 verify. Gross16 verify. And if it doesn't verify, then it returns return M. So this is a circuit that takes the proof. If the proof doesn't verify, it returns the thing that allows you to slash me. Okay? And so at the very beginning, we're gonna have, imagine I'm the prover and you guys are the verifier. We're gonna do this setup between us, and I'm gonna produce this thing, and there's gonna be some proof that I'm producing correctly, basically. And later on, you'll have this thing for yourself, and you'll be able to evaluate that. So in the lingo, it's like I'm garbling the circuits. I'm creating a circuit with my secret M and all these things. You can imagine that every gate is encrypted in that circuit. And later, when I try to spend it in my, this was the setup, I guess. And then I try to spend it here. So I will say, here's my proof. And here's I don't know if I should introduce it here. It's kind of a messy expansion. I apologize, but I introduced some encoding, which basically allows you to evaluate that circuit I gave you during that setup. And you evaluate that. If my proof is wrong, basically that will give you the thing to slash me, the message M. If the proof is not wrong, then you cannot do anything. The time lock will expire, and then I can use my phone. Again, garbled circuit is like a two-party thing, a two-party computation. The nice thing is that it's non-interactive for the evaluation phase. So once we agreed on that circuit, and with some help from me, which is I'm gonna give you the encoding for this argument, the proof, then you can evaluate it yourself. Does that make any sense? Maybe I should clean that up a bit. So there's a lot of stuff here. Did anybody understand what I said? Oh, okay. At least some people got it. Can I clarify maybe? Does it make sense when I say that, like, during that setup, I produced a garbled circuit, which is kind of a box that later on you'll be able to evaluate. And if the proof that I commit to when I try to spend it here, right, I sign this variable, I guess, plus its encoding, I guess, which is just what is the name of that argument in that garbled circuit, let's say. You yourself can evaluate this thing, and yeah, first, I guess you can evaluate this thing. Does that make sense? So that's kind of it was kind of like the epiphany, I guess, of these papers were like, oh, we can move most of the execution off-chain by just agreeing on a garbled circuit during the setup, which is off-chain, like we do this setup off-chain, and we can actually verify the proof within the garbled circuit. Is there anything I should add, I guess, for the people who understand that or already knew that, that would help clarify?
Maybe you can draw like a gate, like AND gate. Help understand.
Yeah, maybe the Garbled circuit you can see as a, you know, you have an entire circuit of like things move like, you know, like that, and gives you something at the end, I guess. And for every wire, this is a binary, a Boolean circuit, I guess. So every wire has like 0 or 1. You don't know in advance what you're gonna get. So you sort of have a duplication. Because it's a circuit that has all the possibilities. So here you have 0, 1, 0, 1, here you have 0, 1, and you don't know which one you're gonna have yet. And basically what they do, when I garble the thing, I basically, let's say I encrypt all of these things. Maybe I replace it with some garbage. So it's like E0, E1, E2, E3. And let's say this is an AND gate. And so you don't really know, when you get the garbled circuit, you don't really know what is what, because it's all like garbled values, I guess, like random values. And usually this is sort of a truth table that tells you like, or I guess I should have kept the encryption here. Or the encoding encryption. Using this, if you know E0 and E2, let's say this is N, right? If you know E0 and E2 and this is, or E1 and E3, this is 1 and 1, then this would allow you to get the value behind E5, I guess. And the way it works is that the encryption key for E5 usually is E1 concatenated with E3 or something like that. So you can use, it's all symmetric cryptography. And but the reason why you cannot evaluate this thing is that you don't really know these values here. So if pi is like 0, 0, I would release these values, I guess. And one of the interesting things is that basically we can use like a hash here, and releasing the values is kind of like signing using a Lamport signature. So when I set the proof here in my transaction, because I want to spend what was locked and I want to commit to that proof, I also have to sign that thing. So there's a public key that was like agreed on in this simulated covenants thing. And by signing it with my Lamport public key, I'm basically releasing the encoding that allows me to sort of execute that circuit by decrypting values, by taking the circuits and decrypting values. And but I don't want to talk about garbled circuits. I guess that's not the. Maybe we should do a session one day on garbled circuits. That would be cool. But that's sort of the idea of garbled circuit. At the end of the day, they give you this like black box magical thing that we can sort of agree on a circuit and what it does. And there's a setup, and at some point you have it and you can execute it. And you don't really know the value M. Everything's sort of like hidden to you, but you can execute it by yourself. That's sort of the idea.
So in that neural line of work, is it still permission? Like it's still very permission, right? Like in the sense that the verifiers have to be known ahead of time.
Yeah. Or at least anytime we look at these papers, it's always like there's a prover and a verifier, and how to make it like permissionless, or how to make it so that like there's a committee is always like more complicated. So like different schemes, I think are. I was listening to a podcast coming here, and they were saying that Babe cannot be permissionless, but like BitVM 3 could be permissionless. You're nodding your head, I guess so.
Like this garbled circuit, Yellow style, you can do it one prover and any verifier, because you just garble it and everybody can verify the garbling if it's done like that.
Yeah.
But the permissions where it comes.
No spoiler. Or actually, maybe it's a good time to.
And most of the times we need covenants, and you cannot do that. So permission set comes from that most of the cases.
Okay.
So I guess here the idea is, okay, so this perfect segue. Here the person garbling the circuit is the prover. And so when they release the encoding, anybody can evaluate that is if the garbled circuit lives somewhere that is easily available, and so that means you introduce like some DA, data availability, and so it's a new assumption. All of these have trade-offs, by the way, but so that's interesting. Okay, so last one, or one more question before, or a comment, or?
Do you have encodings deeper in your circuit than just the inputs?
So you have encodings for, basically everything is sort of encoded or encrypted, right? But you need to know there's a decoding table at the end, which needs to be public. So at the end you get something, right? Like there's two wires, 0 and 1, I guess, and you get them encoded, right? E8, E9, something like that. And you need to know which one corresponds to 0, which one corresponds to 1, basically.
Okay, one more small question.
Yeah.
So specifically, I know that you gave an example of like if not Groth16 verify, then return nil. Have people been looking at like other functions, like not Groth16 verify?
So I mean, there could be more stuff, I guess.
Yeah, just like wondering what's out there.
I mean, we're gonna see that Babe looks at something else, but there's a deeper question there, which is like, yeah, what else could we be doing? And I heard that you can, with the newer schemes, like there's Argomac also that I should have mentioned. Like the GC is getting even more efficient, and so you could think of having like permission stuff in it. I don't understand how you would do that, or like what would be interesting to put there, but it sounds like there's interesting things you can put and interesting schemes you can create. Okay, maybe one last thing, and then I'll move to Babe, but garbled circuits are kind of annoying in that you need to prove, if I'm the garbler, I need to prove to you that I garbled the circuit correctly. I could have put just bullshit here. And so there's different ways of doing that. You can do a ZKP of like correct garbling, but it's pretty heavy. So what people do usually, and that's what the latest schemes have done, they do something called cut and choose. CC, I guess, cut and choose. And this is the most barbaric and horrible, I mean, not horrible, but it's just barbaric and like brute forcey kind of way of doing things, which is like, as the garbler, I generate a bunch of garblings, and then so during setup, you as the verifier come and you just select half of them, I guess. Like randomly, you select half of them and you open them and you make sure that they all make sense. If any of them don't make sense, then you just abort. And then you keep the rest. And then whenever you evaluate your stuff, you will evaluate all of the other ones. So maybe let's say half. And then if any of them give you a different result, then you give up. And so then it's a game of probabilities. Like if someone was trying to attack me, what are the odds that they guess in advance which one I would select and make them correct, and all the rest is incorrect in the same way. And you can do, I guess you can do plenty of protocols this way in real life with this cut and choose approach. So that makes it pretty big for the person that has to store the garbled circuits. That makes it pretty big also to like when you produce all these garbled circuits and you need to store them, and it's quite inefficient. And so reducing the size of your garbled circuits, or there's a real incentive to reduce the size of the garbled circuit. And so that's basically what Babe is doing. It reduces the size of that garbled circuit by reversing who is garbling and who is going to evaluate that garbled circuit. Okay, so bear with me. This is the last step. To do it, they introduce a new primitive called witness encryption. So, something not always lightweight, but the one they introduced is pretty nice. So witness encryption is basically, it looks like a public key encryption primitive where you can encrypt to like a circuit, so like a CRS or let's say, I don't know, let's say CRS, I don't remember I'll get into that. You encrypt something, a message, and then whoever has a witness for that CRS, so whoever can produce a proof because they know witness, this is a ciphertext, can decrypt that ciphertext to give them back the message. So nothing crazy. You can just encrypt to a circuit, and whoever knows a witness to the circuit can decrypt the message. And there's a nice way to do it for gross 16, which is in gross 16. Eventually, you have an equation that looks like pi 1, pi 2 plus. Okay, so eventually what the verifier checks is an equation that looks like that, where there is some like thing they can compute that's fixed on the public inputs. And with two pairings, and that involves pairings, but it doesn't matter. And then with two pairings, one that involves two proof elements, and one that involves only one proof element, and some public stuff that they can compute. By checking that, they know that the proof is valid, right? So just trust me on that. Like, I'm not gonna prove that to you. And the idea is that to encrypt something, you can just take a randomized version of Y. So encryption, you hash for some random R, Y plus your message, and that's your ciphertext.
What's that? Is it hash?
Yeah, that's a hash, or something like you just randomize, or you just encode these things and hash it or produce some uniform randomness. I'm actually not sure exactly how they do it in the scheme, in the instantiated scheme, and then you add it to your message. Just imagine that you can do something like that. And then to decrypt, how would you decrypt? You take your ciphertext and you try to create this thing, right? And then you subtract your ciphertext with this thing and you get back the message. How do you compute this thing? You can compute RY. So let's. So you want to compute RY basically. You could, for example, if the verifier, if the person that encrypted gave you RX, you would already have like the R in these parts. You can compute these things, right? Because you know the witness, so you can create these proofs, so you can create these things. But you don't know R, how to put R here, I guess. Does that make sense when I explain things like this?
If I'm given Rx, I can do the pairing and it will be equal to R times pairing.
Yeah, you would put it here, I guess. Right. And then if you have R and R here, it puts it on the outside, I guess. You can think. Actually, it's more like R here. I mixed the. Oh no, I use the plus here. So no.
It's fine. It's
Okay, so the person that's encrypting can give us this thing as part of the ciphertext. That's fine, but we don't know how to solve this part here. Like if we could put the R somewhere, it would work, but we basically don't know. Like so I'm gonna put it here actually. If we add something like that, it would work, but we don't know how to get that part. So the idea is to replace this thing with R Z, let's call it, which is basically R pi 1, but is known. It's a known quantity now. And so now this equation becomes linear in the witness. And so now you can have a scheme where, and now this works, because you can just compute this thing as the decryptioner. And it produces this value, and you can hash that and subtract the ciphertext with it. The question is, how do you get this thing here? So see, a somewhat simple equation, you can think about it, and abstracting the pairings and everything. You can think about it, and then you can, if that makes sense, or if that doesn't make sense, you can trust me that if you could get R times pi 1, the first part of the proof, then you could decrypt this message. So maybe I'm gonna give you the short answer here, but you can have a garbled circuit to compute that. Basically, this is what you're going to do in your garbled circuit. And since this is a point, they use like special techniques to make it very efficient in the garbled circuits. But this is what we're going to agree on in the beginning is going to be a, maybe I should spell it out. It's going to be a garbled circuit that's going to take pi1, and it's going to return R times pi1. That's the garbled circuit. And it's super, super small and very efficient because of optimizations that they use. And so now we're reversing things. Our protocol up there is going to become, so if you remember, we had the prover that was processing the proof and the encoding, and then the challenger would evaluate some this one here on the proof to get the M to slash the prover in case of a fraud. In this case here, what happens if the in this case I'm the prover. I agreed with the challenger in the future, so there's a specific challenger, I guess. So I got these garbled circuits, and when I'm gonna try to spend what is locked, I'm gonna release pi. Oh, and I guess there's a edge of M that was agreed on at some point. Yeah. So I'm gonna release pi, but I'm not gonna release the encoding because I don't know the encoding. I'm not the person that garbled. And so someone's gonna come here, the challenger is gonna come here, and by producing a transaction that spends one of the output of that transaction, it's a circuit, remember? We're thinking in terms of circuit now. By doing that, they are forced to sign the pi, and so to produce an encoding of the pi. Of pi1, I guess, is one here. Yeah, this is horrible. Up. Transaction 4. They produce, by executing one of the thing, right? They produce encoding of pi1, which will allow you to evaluate, as the prover, evaluate the circuit. And what you get is this quantity. So as the prover, you just got that, which is exactly what you needed to compute this quantity here, which is exactly what you needed to decrypt M. And so now what you can do is you can slash the verifier, the challenger. So they're not slashing you, it's you slashing them this time.
How do they avoid introducing a new trust assumption? Because like as it's presented here, it's just like A multiplied by R, but
A multiplied by
previously it was like actually, hey, let's verify with a set of with the verification key that is specific with circuit. But here it's like, hey, this is not very circuit specific.
So what do you mean, I guess?
So like, how do they avoid introducing the trust assumption about, is this the correct circuit, or?
You mean this circuit here, or you mean the gross 16 circuits?
Yeah, the gross 16 circuit.
The gross 16 circuit?
Yes.
Because there's many circuits, I guess. There's the GC circuit, the gross 16 circuit, the Bitcoin circuit that we create. I guess you sort of have to commit to it at some point. Maybe your GC looks different. Maybe the
it's there, okay.
yeah. I'm omitting a lot of details, and probably it's not secure. If you yeah, when I was looking at this paper, I was like, well, you could also just not commit to pi2 and pi3, and so they challenge you, and then you're like, oh no, actually I know the good pi2 and pi3 to verify that. So you could bait. There could be a bait attack, and there's different things you can think about. But yeah. So I guess I don't have the time to do it, or maybe I can do it. But if you look at the Bay paper, there's actually a nice diagram. If I could display it, I would show you. There's a nice diagram, and they show you exactly the transaction graph that the simulated covenants do. And it's actually pretty simple. It sort of looks like that, but it shows you exactly how you wire things. And yeah. And yeah, I guess I can do a follow-up when I when I explain this. but it's only like 5 transactions, and you can see clearly like this is what you need to show. And so it's a very simpler scheme now. There's like complicated, garbled circuits, and you have to do cut and choose, and you have to do the witness encryption. Like it's complex, but it's very simple in the Bitcoin. Yeah. All right. Any questions on the? Yeah.
Wait, so in this example, R is it's like a toy example, right? Like obviously it'd be a much more complicated.
Yeah, so if you want to do like actual applications that are interesting, like a bridge or like a ZK rollup or these kind of things, then you need to figure out, okay, like in these examples, we're like a prover and a verifier.
Yeah.
And also in this scheme, the public inputs are fixed ahead of time also. So like you have some constraints. You sort of traded a set of constraints for another set of constraints, and then you have to figure out how do you build a bridge on top of that. And I guess Citra is doing a lot of that. And oh yeah, okay. So yeah, also like this field is moving quite fast. Like it reminds me of like ZK back in the days. It's like there's new schemes happening all the time, and yeah.
I guess even that garbled circuit takes gigabyte of ciphertext if you want to do it naively, like YAO style.
Right.
But if you add Argomag on top of that, then you can have like megabyte size garbled circuits.
Mm-hmm.
Yeah, they say it's like, I don't know, 5 megabytes or something like that, instead of gigabytes of circuits. Maybe the first one were like 50 megabytes or 50 gigabytes. And
you need to split it across blocks, or actually you wouldn't, because those
this is off-chain for you to store. And yeah, so I think their technique is like, instead of doing like binary, like a YAO garbled circuit where you go down to like binary stuff, you just try to keep it at the structure of a point, and then you can do your GC on that. But I don't know how that works. Yeah.
If it's on the order of like megabytes, why wouldn't you stick it on chain in a block if like 4 megabytes is the limit, and then you're at? Or maybe that's a dumb question.
No, it's a good question. I guess because it doesn't matter, because only the prover can evaluate that, because they're the only one that that wants to decrypt with the witness encryption scheme. Yeah, this is good. That's how we understand the thing. We have to ask questions like that. Did that make sense? You understand Babe now?
Yeah.
Which is Babylon Berkeley. That's what I heard today.
Super basic. So the verifier provides this garbled circuit. So you would say that they now agree on this garbled circuit, but the prover does not know R.
Yeah. So that's why I'm saying like you have to see it as a black box that you can evaluate yourself, but you don't really know what's in it.
How do you do that? Wait, R is private, and as an evaluator, you don't know R?
Yeah.
But when you execute the garbled circuit, you can compute R times.
Yeah. That's the magic of MPC, right? Like you don't know one of the inputs, which is R. And that's why during the cut and choose, you have to like, every time you have to create that transaction graph, and you have to verify that this is the, every time I guess you have to use a different R, because you're opening these circuits, you need to verify that this R corresponds to the witness encryption one. So that's how you make sure that the R is correct with the cut and choose approach. So you don't verify that it's going to be correct, but you assume that it's going to be the correct R. As I'm saying that,
Something like oblivious transfer for that? How did you?
So you don't need oblivious transfer, because oblivious transfer would be like, I want to evaluate that garbled circuit, but I don't want to tell you what is my input. So you would give me the encoding obliviously without knowing what you're giving me the encoding of. Here, it's completely public. Like I sign the proof element 1 on chain, and then I reuse it here, so I know exactly what I'm encoding. But about the stuff I said previously, you need the same R in all of the. If you do cut and choose, you need the same R everywhere, because you're gonna evaluate all of them. And it's supposed to give you the same. Anyway, I don't know. Yeah.
So the verifier in advance decides a bunch of R's, and then they kind of provide all those garbled circuits. Maybe this is a crazy question, but like someone else knowing that can't then pretend to be the verifier and then be spending the UTXO.
You can't evaluate that until the prover comes and create that transaction. And by the way, only the prover can create that transaction. Like they agreed on that with the simulated covenants, that only you need a signature from the prover and the verifier to create that transaction. You know exactly who's gonna get paid, like all these things. And so only when you create that transaction do you see that point. And that's only when you see that point that the verifier can come. I think it's called in the paper they call it assert transaction. Assert. Then the verifier comes, they create this challenge asserts for if you want to look at the paper after. Challenge asserts. Then there's a time lock. So there's a time lock here, right? Like to use a TL time lock. If you don't use that, then you can use it to spend here, I think. There's a time lock here. Oh, no. Yeah, sorry. If the prover doesn't say anything, then there's a time lock, and it goes to no withdraw. A transaction called no withdraw. Withdraw. Basically, if the prover doesn't answer, then the time lock expires, and we use that UTXO to spend it here. And this UTXO we used here, so it cannot be used here anymore. Wait, no, that doesn't make sense. I don't remember the graph, but if we looked at the paper, it would make sense. But it's sort of like there's always a time lock. Then if you assert, you have to you have to run a circuit here that will encode this thing, but with the Lamport signature stuff. If the prover doesn't answer, there's no withdraw. If it answers, you can use the same UTXO to a challenge failure, I guess. And then it sort of goes back to the first withdraw transaction. I can't remember how they did that, but it's yeah. We can look at the paper together if you want.
There's one idea that you don't need to have these proofs happen with the funds. You can separate those, and you can do this thing called connector outputs, where if it gets disproven, the output is burned, like it's spent. But if it's not spent, later at that time, you can use that output with the covenant to take the funds to somewhere else. So the funds are pre-signed with another input, which
Right.
is just zero value.
So that's how we do it. Like this output will go to your transaction to spend it if the time lock happens. But if you do a no withdraw, you can use that output here, and this will either burn the output or send it to the verifier. You can do whatever you want. But so that output has to be used either to withdraw it or the verifier wins the challenge and they use it. So I guess it's called a connector output.
So that's auxiliary to this is connector outputs.
Yeah, I guess it's one of the technique that I was explaining earlier. It's how do you keep variables across? How do you branch, depending on what you do? So connector output, I guess it's part of the simulated covenants, kind of.
Yeah, it's one way to have a state between scripts as well, I guess.
Or to circuitify. I see that as a circuit. That's how I think about it. Yeah, and I see the signing variable stuff as like SSA. It's like compilation. All right, let's stop here. It's lots of circuits. That's all you need to remember. All right, cool. Thanks. Did we finish all the pudding?
Yeah, I guess. All right.
Damn it. Ah. Is there more?